Hello and welcome to Build Your Own CPU Part 5. In this episode we'll be looking at the adder. Here's the top nibble, as can be seen by the 4 links on the right, and the carry in on the top left. This feeds down to the lower nibble, so on the right you've got 4 links for the lower part of the byte, and on the left you've got the carry out signal. This is fed via the B control register, which does your inverting of the signals and zeroing of any values if needed. Now, standard full adder circuit is this. You find it all over the internet. If you've got one input on, then your sum will come on. If you've got 2 inputs on, your carry out will come on. If you've got 3 inputs on, you'll get sum and carry. And of course, if you've got no inputs on, you get neither sum nor carry going out. Now, one thing about this circuit is, if you're doing this with ICs, it's fine, but if you're doing it with transistors, doing an AND and an OR is quite easy, but a XOR gate, well, that's a bit different. U1 and U2 are both XORs. So no straightforward, well, there are some straightforward transistor circuits for doing those, but generally, this is what your circuit would be. This is an XOR. You'd have to use an OR gate, an AND gate, and an AND gate just to perform the same function as an XOR. So if A and B are off, you get a 0 out. If A or B is on, you get a 1 out. And if A and B are on, you get a 0 out again. So you just want to know if one of them's on. So if you put that into the previous circuit, you get this. It's a full adder, built the same, but using ANDs and ORs and NOR gates and AND gates instead of an XOR. So you may notice there's quite a few gates involved here. Now the numbers within each gate is how many transistors in CMOS you need to build that gate. So in total, one bit of an adder would be 50 transistors. Now I've got a limit on how many transistors I can put on each board because my circuit diagram program, or circuit board making program, my license only lets me put a maximum of 500 points on there. So a transistor would be like 3 points because it's got 3 legs, a resistor would be 2. But they all add up. And it takes space. So I can generally get maybe 130, 140 transistors at the most on one board. So with this, I could only get 2 of them on. 2 bits I could do on one board. So I'd end up having to have 4 boards. So 4 adder boards doing 2 bits each, plus the B control register, plus the B register and the A register, and the control register above it. That would be a total of, what, 4, 5, 6, 7, that'd be 8 boards high. So that's 0.8 of a metre. Makes the whole circuit a bit tall. These are making it a bit more rectangular. One advantage of this circuit though, is you have this. You've got A or B, you've got XOR A and B, and A and B. So you don't need an OR, XOR, or AND circuit board to get these functions. You can pick them all off the adder. Of course, having these outputs on the board, there'd be another tri-state buffer for each of these. That's another 4 transistors each. Well, actually, since it's inverted, it'd be 6 transistors each. So that's even more transistors. So what I decided on is this circuit. Again, I found this on the internet, I didn't invent it. So this uses 28 transistors to do an adder, but you don't get the AND, XOR and OR functions. They'd have to be on separate boards. But what I can do is I can fit 4 of these on one circuit board. Therefore, I only need 2 adder boards to do the full 8-bit adder. So these are the actual transistors that do the adding. I mean, you can go through all the logic of what ones do what if you want. It's a little bit confusing. It gives a carry out, so that can feed onto the next bit. And there's a carry in as well on the left. The one adder feeds onto the next. And when you get to the end of the board, you just feed that board off onto the next one. So you can daisy chain them. I mean, I've done an 8-bit adder. You could do 12, 16, 32, whatever you like. The transistor's not highlighted here is just for the output signals, you may notice that you've got a tri-state carry out. Well, that is only on one of them. That'd be on the very last board when you've got your final carry out. That is got a tri-state on it because other boards doing other functions can also set the carry flag. So you have to be able to switch them on and off to isolate them from each other. So here's the actual adder that I built. You notice there's 4 of those circuits we just had, and only one carry out at the top. So one board does either bit 0, 1, 2 or 3, and the next board does bit 4, 5, 6 and 7. So there's a total of 130 transistors on that board. On the left you can see the A bus, AR bus and the BR bus coming down there, and you just pick off which bit you want. Right, here we have the bare board for the one nibble of the adder. So over here we've got the adder output enable, the C input, 0 input, that's the carry or the C register input for bit 0. Here we've got the C7 output, so that's the 7th bit that comes out of there. It won't actually come out of this board, it'll come out of the second one. So carry comes in here. This is active all the time, so whatever's coming in is being added up. We only control the actual output. So at the top here we'll have the A register coming the top up here through these 8 bits. You run down through here, on the back there's a long bus that runs straight through. And so if you're doing the top nibble, we'll pick off which bit is in there. If you're doing the top nibble, we'd have links across to there. And that one, and that one, and that one, and as they get shorter. If you're doing the bottom nibble, as in D0 to D3, you'd be coming from here, the link will come from there to there. So basically you just select which input you want to the 4 adder modules. All these transistors down here are there's tri-state outputs, which the adder output controls. And these are the nibbles going out to the data bus will be down here. So you either have top nibble or bottom nibble going out. There's some LEDs here as well, so you can see the bits going on and off. Over here we've got the power supply coming in and the decoupling capacitors and magic blue smoke resistor. Here you'll notice there's another C in 0. That's the same as that one, actually in parallel. This is if you're feeding in from a board above. And here down the bottom you've got the C7 out. Which will actually be C3 out if we're going to another board. If we bring another board over, it'll make a bit more sense. Let me just zoom out on this. There we go. So you'd have 2 boards like this, all we have. So the A register comes in here, feeds all the way down, and then links across to the bottom board as well. B register will come into the bottom down here, you can see at the bottom. And that would feed all the way up and links across here to feed up to this other nibble. So this would be, say, D0 to D1 coming out here, and this one would do D3 to D7 coming out here, and you just pick off which outputs you want onto your data bus. So the carry from this board will link across to here to carry on through these, and the output from this one doesn't come from here, comes from there, and the input comes up there, as you can see on the main board. So that's how the adder is. To be able to do addition, subtraction and increment the program counter, we need to be able to control the B register going into the B bus of the adder, B input of the adder. So we've got this circuit on the B control board. We've got the add function, so when we're doing an add, the add control line will come on, and that will switch data from the B register straight through into the B port of the adder. And if we're doing a subtraction, we have the sub control line comes on, and you may notice that the data coming from the B register goes through an inverter before going out to the adder. But also if we want to increment the program counter, we want the B input to the adder to be 0. So we've got this circuit, it says B clear, but really what it means is the B input to the adder is cleared, all to zeros. So to do an increment, we put the value into the A register, we set the C register to 1 and the B register to 0, and then sample the output of the adder, and that will be the A value plus 1. So we use this for adding 1 to the program counter. So this is the actual circuit of the B control board. You've got data coming in from the bottom, goes across, and when you've got the add control signal on, transistors Q1 and Q2 will switch on. You notice they're both NMOS transistors. It feed through the diodes. If it's a 1, it will go through the top diode and Q1 and out to the B input of the adder. And if it's a 0, it will be pulled down via Q2. Now if we're doing subtraction, you see we use the lower circuit, but there's an inverter just before it made out of Q6 and Q7. So the value from the B register gets inverted. Again, that gets fed out through Q3 and Q4 and the associated diodes into the B input of the adder. So we've now got an inverted signal. 1s become 0s and 0s become 1s. And when the B clear signal comes on, which doesn't actually clear the B register, it just makes sure that the B input to the adder is pulled down to 0 via Q5. So B would be 0 then. Now we need to do subtraction. So we saw that the sub signal inverts all the signals. So imagine we've got 10 minus 3. What we do is take the 3 and we invert it. So all the 1s become 0s and all the 0s become 1s. And then we add the 10 to it. And this gives us an answer of this. You notice the carry flag is on, but also you notice it's the number 6, not the number 7. The answer should be 7. Well, you have to make sure that the C register is set. There is a control signal that says C set. So C register would be 1. So you're going to add A, B and C. So A being 10, B being the inverted 3, and C being set to 1. And that gives you an answer of this, which is 7, which is the correct answer. Now the carry flag is on to say that the value is positive, if you need it. If you're just doing sub with borrow, then you'll be needing that. Let's go through that again, because you think, well, just this 1, does it work just the once? Well, no. So we've got 33 minus 10. So there's 10. There's the inverted 10. There's add 33 to it. And we get this number here, which is not 23. It's 22. Again, the carry flag is on. So there's the 1 we have to add from the carry, which brings it to this value here, which is 23. So we've got a positive 23. Now let's do a subtraction where it goes negative. So we've got, say, 33 minus 44. There's your 44. We'll invert it. Then we add the 33 to it, the same as before, which comes up with this answer here. The carry flag is a 0 now, so we know we've gone negative. So we've got to borrow. There's the 1 from the C register added on. It gives us a grand total of minus 11, or 245, depending on how you view it. So we know that's a negative 11 because the carry flag is a 0. So again, if you was doing the sub with borrow, this is the whole value you'd use in your next instruction. Here we have the B control board. So over here, got the supply coming in with this time the decoupling capacitor at the bottom for some reason, and the Magic Blue smoke resistor. Over here we got the sub, add and B clear signals. So these transistors down here, if the B register comes in here, these are the inverters. So we've got 16 signals going up rather than 8. Got the 8 normal ones come straight through, and each one of these is one bit of the switching circuits. So here we'd have a direct in, or the inverted signal switched out to the B register, or these are the transistors at the bottom. Is where you're switching it down to 0 volts to give you 0 out there. So this board, we zoom out again. So you do it like this. So the B register would actually be connected down here at the bottom, and will feed up through whichever circuit you want into the B port of the adder, linking across here, and your supply just linking down there, down all the boards. So that's it for this episode. So don't forget to like and subscribe, and hopefully I'll see you in part 6.